Hey, what's up, everybody? We are back on Mr. Murray's Mathland and continuing on with derivatives of these functions with bases other than e, in this case exponentials. And prior to this point, the only exponential rule you've learned is for e to the x. And so let's just recap that because it's very closely related to it. So hopefully you feel pretty comfortable because the derivative of e to the x is e to the x, right? That's a rule that you've hopefully used many times by now and feel good about. So when you're taking the derivative of, say, something like 11 to the x, it is an exponential, so it probably has a pretty similar rule, right? Maybe you're thinking it works out to just be 11 to the x. And of course, it's never quite that simple, but I do like to, kind of prove this one. Again, from an AP standpoint, what if you forget the rule, you're on the exam, you have no formula sheet? So you could do this on the spot if you forgot the rule. You could take this and convert it to something you're comfortable with, and that would mean let me take the log of each side. But which log would we use in calc? Almost always ln, natural log. So if I take the natural log of each side, I'll get ln of y equals ln of 11 to the x, and that allows you to then use your power property and bring that x out in front. So here's what you're looking at now. You have ln of y equals x times ln of 11, and I'm just going to rewrite this as ln of 11 times x. So we're really emphasizing that that's just a constant coefficient times x, no different than doing the derivative of 7x. So now when I differentiate that, I'm going to take the derivative with respect to x. The derivative of ln of y, see, I'm using implicit differentiation now. So the derivative of ln of y is 1 over y times dy dx, right? Over here, the derivative of ln of 11 times x is just ln of 11, right? No different than derivative of 7x is 7. And so when I solve for dy dx, you just end up multiplying by y. So you get ln of 11 times y. And in this problem, what is y equal to? Y is equal to, if you go all the way back to the beginning, y is equal to 11 to the x. So this derivative ended up being ln of 11 times y, which is just 11 to the x. This is what I came up with here. So notice when we kind of thought about maybe it's a similar thing where you get that repetitive function. That is true. But you get this additional little constant multiple of ln of that base. And so that's really the rule there, that the derivative of a to the x is going to be a to the x, but multiplied by ln of a. And that even, of course, would work for e, if you must apply, because the ln of e is just 1, so it's not really necessary. So there it is. Kind of cool, and kind of cool to derive it, I think. But now, hopefully you just know it and you can use it. You don't have to derive it on the spot. You want to save time where you can in general. So I mix it in here with a trig function, the derivative of y equals 3 raised to the tangent of negative x. So again, just to bring that rule back here, that the derivative of a to the x will be ln of a times a to the x. You'll get that repetitive a to the x, but times ln of a. So y prime will be, if it's 3 to the tangent of negative x, you get that same 3 to the tangent of negative x. Just like when you use your e rule, you get that same function right back, but you are going to also be multiplied by ln of 3, always. And if that exponent isn't just plain old x, then you have to use the chain rule. So now I have to multiply by the derivative of tangent of negative x. Derivative of tangent of something is secant squared of that same something. And on the inside of there, it is another chain rule, a little chain rule, but multiplying by the derivative of negative x, which is negative 1. And so maybe this would look nicer as negative ln of 3 secant squared of negative x all times 3 to the tangent of negative x. Maybe that looks a little nicer. There's no great order there for that, but that's it. All chain rules accounted for. And number 2, how about using it to do a classic tangent line kind of problem, writing the equation of a tangent line. And, this isn't a crazy rule that comes up a lot, so that's why I'm, keeping this 2 examples pretty simple here, not making them too elaborate. I think on an AP exam, there might be 1 question about this typically. Sometimes there might be none, but, but still, it's good to know. And if they appear, they're usually pretty easy on the AP exam. It's not a big, elaborate part of a chain rule and implicit and all that kind of stuff. So tangent line, we need 2 things, right? We need the point. So I need that y coordinate for my point of tangency. So I'm going to plug in log base 5 of 2 into this function. And I'm intentionally bringing this back to review some log properties. So I'm plugging log base 5 of 2 into this. So we have 5 to the negative 3 log base 5 of 2 all minus 7. And if we were on a multiple choice, this would certainly be simplified by using some log properties here. I'm going to take that negative 3 and make it a power of that 2. And, if you know where I'm going with this, you're probably way ahead of me. 2 to the negative 3rd is really 1/8. And we want that because if you notice, this is 5 to the log base 5. And so those are inverse operations, exponents and logs. So if they have the same base, they will always cancel each other out. So you are going to get just 1/8 minus 7, and so that's going to be, if you want to do a little common denominator here, 1/8 minus 56/8, negative 55/8. Nice numbers here, right? These are nice points here. So this point is, the x-coordinate is log base 5 of 2, comma, negative 55/8. All right, there's our point of tangency. We haven't done any calculus yet, just some nice pre-calc. And so now let's get the derivative in order to get our slope. So the derivative of this function here, I'm just rewriting it because it's near the top of the screen in case it gets cut off here. So there's the f of x here. And so f prime would be, it's an exponential, that's not e. So you're going to get ln of 5, ln of whatever that base is, times 5 to the negative 3x. You always get that repetitive nature, that function right back, and times the derivative of that exponent. So also times negative 3. And of course, minus 7 is a constant, so its derivative will just drop out. And so maybe your function looks better to be a little cleaned up like negative 3 ln of 5 times 5 to the negative 3x. But now you got to get that slope at that x value of log base 5 of 2. So f prime of log base 5 of 2, negative 3 ln of 5 times 5 to the negative 3 log base 5 of 2. And we're seeing that same kind of expression right back again. So I'm going to do that. Move that negative 3 to the top. And this is negative 3 ln of 5 times, and that is of course going to make 1/8 again, and the log base 5 and the 5 to the cancel each other out. So you get 1/8. And so maybe that looks a little nicer as negative 3 ln of 5 over 8. That is your slope. So there's your point, there's your slope, right? And so your tangent line would be y plus 55/8, y minus that y coordinate, right, equals negative 3 ln of 5 over 8, the slope, times x minus that x coordinate, log base 5 of 2. Yeah, have an Algebra 1 student grade that, graph that line right there. Very nice. Okay, so hopefully you saw a couple examples. You feel comfortable with using this rule. It's just a basic twist on the e to the x rule. and threw in a couple chain rules and trig and a tangent line just to keep all those ideas fresh. But if you have any questions, let me know, and otherwise, keep on working hard, and we'll see you soon.